when we were doing 1D kinematics, we had all these equations that we could apply as long as acceleration was constant. In 2D kinematics, the same equations apply, and they apply separately to the two directions of motion. So all of these equations apply in both the x direction and the y direction. So delta x is v average in the x direction, we put a little subscript x, times t. Delta x is also 1/2 v naught x plus v final x t. Acceleration in the x direction is delta vx over t 2a sub x equals delta x times delta x equals v final x minus v naught x. X final equals x naught plus v naught x plus 1/2 a sub x t squared. And then the same equations also apply in the y direction. And it's interesting that the two directions of motion are completely independent. So what is happening in the x direction, y, has absolutely no bearing on what's happening in the y direction. When I say that, that means that an acceleration in the x direction doesn't affect the motion in the y direction at all. A velocity in the y direction doesn't affect the x motion at all. T squared. Right. So all of these equations we can apply in 2D kinematics. Most of the time, we're just going to use these two. And sometimes this one. But the others don't pop up as much when we're doing 2D kinematic problems. Most of the time, also, when we're doing 2D kinematics, what we're going to be talking about is projectile motion. And the reason this is so important is because projectile motion describes how any object moving near the surface of the Earth behaves. Okay? So near the surface of the Earth, we can take these equations, but kind of reduce them a little bit. So when we say projectile motion, what we're referring to is an object that's thrown or fired out of a cannon or a gun or a slingshot, anything that's traveling through the air and not being actively propelled by anything. So once the bullet leaves the gun, there's no force being added to it. There's no force being applied to it. It's just flying through the air. And the same thing if you throw a ball through the air. Once you let go, you're not applying any more force to it. Okay? So in that case, these equations become much simpler. Generally speaking, we can call our x naught 0, just like we did with most of our 2D kinematic problems. And so we can say that our x position is equal to v naught x times time, and the acceleration in the x direction. Well, if an object is flying through the air, it follows kind of a parabolic path. If an object's flying through the air, the only thing accelerating it is gravity. And gravity acts straight down, which means that the acceleration in the x direction is 0. We can take x naught, set it to 0, and the acceleration in the x direction is 0. If we look at our y equation, it doesn't reduce quite as much. We could start at some position above the ground. Generally, we want to call it ground 0, so we could, we are often at some height above the ground. We will have some velocity in the y direction. But now, again, I said our acceleration is gravity. So our acceleration in the y direction is 9.8 meters per second squared down. So our a sub y is minus 9.8 meters per second squared. Typically, we call down negative, and so then we've got half a sub y. That becomes minus 4.9 t squared. So in the case of projectile motion, our equations reduce to this. And these equations govern the motion of objects flying through the air. Now today we're going to look at two special cases, and those two special cases will make the equations even simpler. The first one we're going to look at is zero launch angle. Zero launch angle meaning that we have v naught, some initial velocity at 0 degrees above the horizontal. So something is just being fired straight out, like a gun's being fired straight, somebody throws a ball straight, whatever. So what happens then? Well, if v naught is at 0, we know how to break it out a vector. Our v naught x is v naught cosine theta. Our v naught y is v naught sine theta. My pen is dying. The components of our velocity are, well, if theta is 0, sine of theta, or sine of 0, is 0, and so our v naught y is 0. So in the case of 0 launch angle, meaning something's fired horizontally, or at 0 degrees above the horizontal, whatever, then our equations are even simpler. That's our x equation, and our y equation just becomes this. Now, this should look pretty familiar. This is just free fall, which is kind of a strange thing. Some people have trouble wrapping their minds around this. The y equation is just as though the object is in free fall. So you could fire a gun, beautiful gun, the bullet comes out of the gun. All right. So there's this bullet coming out of the gun, and this is my beautiful drawing skills. And it will follow this path as it goes down, and the time it takes to hit the ground is the same as if we just take a bullet and drop it from that same height. We can just take a bullet and drop it that same height, and the equation will be the same. In this case, the v naught x is 0. In this case, the v naught x is something, and it'll wind up in a different place. But the amount of time this takes is only in the y direction, and so that's all that matters as far as the y direction goes. Okay, so let's add some parameters. Let's say horizontally from 1.7 meters above the ground. How far away does it land if its initial speed is 89 meters per second? And this is kind of a typical projectile motion problem. Now, we want to know how far away does it land, okay? And when this question is asked how far away does it land, it's just talking about the x distance. You don't need to worry about finding the hypotenuse or whatever. We're just talking about the x distance. So we know we can find the x distance by taking v naught x times time. And we know that v naught is 89 meters per second, but we don't know what time is. So that means there's going to be another step to figuring this out. And this is a common theme in projectile problems. You'll use the y equation to solve for time and then plug that into the x equation. So if we look at our y equation, our y final, it's hitting the ground, which means that our y final is 0. Our y naught is from 1.7 meters minus 4.9 t squared. And we can do some quick algebra to solve for t is 589 and so on seconds. And then we want to find how far away it lands, so we plug that in up here. X is just 89 times that 0.589, which comes out to approximately about 52.4 meters. And remember, we don't care about sig fig, so I'll just leave it as 52.4. You can put more decimals if you wanted. That's how far away it lands. Another common question in projectile problems is, what is its final velocity? And remember, velocity is a vector, so if I ask for final velocity, I'm really looking for a magnitude and direction. Okay? Well, we know that in the x direction, there's no acceleration. And if there's no acceleration, acceleration is delta v over t, so if there's 0 acceleration in the x direction, the change in velocity is also 0. So we know, and this is a general feature of projectile motion, that v final x the final velocity in the x direction is equal to the initial velocity in the x direction, because in projectile motion, the acceleration is only gravity, and gravity goes straight down. It is entirely in the y direction. And so in this case, that is 89 meters per second. Well, we also want to find the final y. And how can we go about doing that? Well, I see that we know our acceleration in the y direction is minus 9.8. We know our change in y, actually I'll go over here, is that height difference, which was, what, 1.7 meters. We know our v naught y is 0, we know v final y, so we could do that. This one we could also use because we have already solved for time. Since we've already solved for time, this is easier because we're just multiplying two things together. This would work too, just a little bit more that goes into it. If I first asked you what is its final velocity right as it hits the ground, then you would have to jump straight through this equation, or else you'd have to solve for time first. Just as with 1D kinematic, there are multiple different ways you can go. Sometimes one way is easier than another. I'm going to go ahead and just use the acceleration in the y direction equals delta v sub y over t. And we know our acceleration in the y direction is minus 9.8. Make sure you keep that sign in there. Use consistent signs whenever we're solving one of these problems. Our final velocity in the y direction is what we're trying to figure out. Our v naught y is 0, and our time is 0.589, etc. And I plug that in using stored value to get that my v final y is minus 5.77 meters per second, 77, etc. And why is it negative? It's negative because it's moving downward. The y component of its velocity is downward. But now when I ask for final velocity, velocity is a vector, so we need to find magnitude and direction. V final, of course, is square root of v final x squared plus v final y squared. And the angle it's traveling at is the inverse tangent of v final y over v final x. We don't care about sign, when SIGN sign, when we're doing this. We know that the x component is positive, the y component is negative, and so that means the vector is pointing off into quadrant 4, and we call that below the horizontal in this case. So we can punch those numbers in. It is 89.186, etc. meters per second at 3.71, etc. degrees below the horizontal. Now you notice that this final velocity is very, very close to the initial velocity. The reason it's always good to do the sanity check at the end. Does this answer make sense, or should I go back and look at my calculations and see if I've done something wrong? Well, this 89 is very close to the initial velocity. It's 89.1, this is 89, right? Well, if we think about it, 1.7 meters isn't all that far to fall down compared to something going 89 meters per second. It would do that really quickly. It would travel much more horizontal distance than vertical distance. And in 1.7 meters, it's not going to accelerate to getting a speed of anywhere close to that in the y direction. And so having a final velocity that's very close to the initial velocity makes sense. Having this really small angle makes sense because it's still traveling more in the x direction than it is in the y direction.